These are the notes for AP Calculus on the topic of the direct comparison test and the limit comparison test. So for the direct comparison test, notice it's referred to as a comparison test. Compare it to the series to another series that's similar to it. And because of that, this is always used in conjunction with another test. So here's what the direct comparison test says. If we have two different series, notice one of the series has a formula to get each term of a sub n, the other has a formula of b sub n. And it says if 0 is less than a sub n, which is less than or equal to b sub n for all n. So if that's the case, that means a sub n is always less than or equal to b sub n. So that's the smaller of the two series. And b sub n is always greater than or equal to a sub n. So that's the larger of the two series. Okay? And this is for all n, so for all the terms, that's true. So what this first one is saying is if the series with the larger terms converges, that's this one, then the series with the smaller terms, that's this one, converges. So let's see visually why that would have to be the case. Well, if we just do a little sketch of kind of what this could look like. As we head off to infinity, if we know the series with the larger terms converges, so let's say that's our b sub n, in order to converge as it heads off to infinity, it has to approach a specific limit. So visually that would be like having a horizontal asymptote approaching with some limit L. So if it converges, that means it's approaching, it's not going off to infinity, which would mean it diverges, it's approaching some specific limit. And then we know a sub n is always smaller than b sub n, right? So if we draw that, a sub n would have to be below, less than or equal to b sub n. So notice what happens. Since b sub n converges at some horizontal asymptote with a limit L, a sub n would also have to converge, because it could converge at the same place, L, or some horizontal asymptote that's less than L, but what it can't do is diverge, because in order to diverge, it would have to go up to infinity, which means it would have to go above b sub n, which we know is never going to happen, because it says a sub n is always less than or equal to b sub n. So it has to stay below it, hence it also would have to converge. Now it also works kind of the other way around. The other way we can use the direct comparison test is if the series with the smaller terms diverges, then the series, that's our a sub n, then the series with the larger terms would also have to diverge. So to kind of get a conceptual understanding of why that would be, let's again draw a little sketch of what this could look like. So this time, our a sub n, the series with the smaller terms, diverges. So as we head out like this for a sub n, as n goes to infinity, this one approaches infinity. It keeps going up forever. There is no horizontal asymptote. And we know b sub n is always larger, greater than or equal to it. So b sub n would have to stay above it. So what this is saying, since a sub n diverges, it goes to infinity. B sub n would also have to diverge because it has to stay above a sub n. So there's no way it could approach some specific limit that's finite, because then a sub n would actually have to cut through it and be greater than, which we know is not going to happen because b sub n always stays greater. So since a sub n goes to infinity, diverges, b sub n would also have to approach infinity. So that's what that's saying. Okay, so let's see how this works on a specific problem here. So it says determine whether the series converges or diverges. The first thing we're asked to do. And then specify what test you're using, or tests. That's what the parentheses S means, one or more. And we are going to always have to use more than one test when we're using a comparison test. All right, so what do we compare this series to? The key is you want to compare it to something similar to this with a direct comparison, and that we can tell is either going to be always greater than it, or always larger than it, or always smaller than it. And notice what we can compare it to. The thing that matters the least in this formula here is this plus 1 that's added to the denominator. So what we'll compare it to is the series from n equals 1 to infinity, infinite series, and of just everything but that plus 1. We'll leave that out of our formula, so it'll just be 1 over 2 to the n. Well, let's first think about which one would be larger and which one would be smaller, because that matters, which ones are a sub n, which ones are b sub n, the direct comparison test. Well, if you add 1 to the denominator, since it's making the denominator larger, that's going to make each term smaller, right? So this one, because of that plus 1, is always smaller than the one we're comparing it to. So if that's the case, since this one's always the smaller one, this one is like our a sub n, the smaller of the two, and this one is like our b sub n, the larger of the two. So we have to figure out, well, is there a way we can tell if this one we're comparing it to converges or diverges? You want to compare it to something similar to it that's easier to use one of the other tests on. In this case, you might already recognize what type of series it is, which is fine, but if not, let's go ahead and find the first 3 terms of this infinite series. So starting with n equals 1, if we substitute in 1, that's going to be 1 over 2 to the first, that's 1/2. If you substitute in the next integer 2, 1 over 2 squared is 1/4. And the next integer 3, 1 over 2 cubed is 1/8. So look at the pattern here. With the 3 terms, you can tell what it is. Notice the numerator is being multiplied by 1, the denominator is being multiplied by 2. So that means it's a geometric series. And the common ratio, what it's being multiplied by each time to get to the next term, is 1/2. And remember, with a geometric series test, to see if a geometric series converges or diverges, this common ratio has to be between -1 and 1. And 1/2, in fact, is between -1 and 1. So that means the series we're comparing to, the 1 over 2n, this geometric series, converges. So the larger one converges. That's like this first case. We know the larger one converges. The series with the larger terms converges. So the series with the smaller terms, since this one's always smaller than it, it would also have to converge. So our answer here would be determine whether the series converges or diverges. It converges. And then specify the test you're using by, well, we use the direct comparison test. And we also use the geometric series test. Again, we always have to use these comparison tests in conjunction with another test. And the other test we're using on the series we're comparing it to. So, and the geometric series test. Okay, let's take a look at one more using the direct comparison test. So again, this says determine whether the series converges or diverges, and specify what test you're using, or tests. So on this one, notice, you can compare it. It would be simpler. This plus 1 is, when you go off to infinity, is fairly negligible compared to n and n squared. So we'll compare it to the series without that plus 1 on the numerator. So from n equals 1 to infinity. And without that, we would just have n over n squared. So let's first see which one's larger, which one's smaller. Well, this plus 1 on the numerator, if you add 1 to the numerator this time, that's going to make this one always larger than the one we're comparing it to, right? Since we're adding 1 to the numerator. So we can say this one is always larger than this one. So that means the one that's always larger, remember we called b sub n? So our original one is b sub n this time. And the smaller one is the one we're comparing to, a sub n. But this series can be simplified. Notice this is the same as the infinite series, the sum from n equals 1 to infinity. And that reduces to just be 1 over n. Same thing, right? And notice with 1 over n, you should notice that this fits our p-series test. And notice the exponent there on the n is 1, so p equals 1. And remember the p-series, since p is less than or equal to 1, in this case it's equal to 1, that means on the p-series test this diverges. So what we have here is this one with the smaller terms we know diverges. So let's look back here. Remember, if the one with the smaller terms diverges, the one with the larger terms, since it has to stay above it, would also have to head off to infinity and diverge. So this one, our series here, diverges by the direct comparison test. And the p-series test. Again, with comparison tests, you always have to use another test along with it for the series you're comparing it to. Okay, let's look at one more comparison test. Works a little differently than the direct comparison test. And it's called the limit comparison test. But again, since it's a comparison test, this one, just like the direct comparison test, is always used in conjunction with another test. Okay, so this time we've got two series. Again, we're going to call the formulas a sub n and b sub n. But this time, unlike the direct comparison test, you can use the limit comparison test even if one is not always going to be larger than the other, or if we don't know whether one's going to always be larger than the other. So it's a little more flexible than the direct comparison test in that sense. So if these are both infinite series with just positive terms, so they're not alternating, it's not an alternating series, where they go back and forth between positive and negative, then what you can do is find the limit of the ratio of the two. And really we could treat either one to be either, but just to be consistent, I'm going to make a sub n represent the original series, and b sub n represent the series we're comparing to. But really it could be either way. So if that equals, if we find the limit as n approaches infinity of the ratio of those two formulas, and we get some limit L, if that limit is greater than 0, in other words positive, and it's not infinity, positive infinity, what that's basically saying is that it's a positive finite limit, so non-infinite is finite. If you get some positive number that's not infinity, then what that tells you is these two series either both converge or both diverge. They have to do the same thing. So let's see how that works on a couple example problems. This first one says use the limit comparison test to determine whether the infinite series converges or diverges. So notice, unlike the other ones, the limit comparison test on this one, it's not going to be easy to tell what we compare to with all these extra terms if it's larger or smaller than. But again, think about when you're comparing it, what's going to matter as n heads off to infinity? Well, it's going to be the terms with the highest exponents, right? So we don't have to worry about which one's larger or smaller, because again, that's kind of hard to tell. But these are the terms, as we head off to infinity, that are going to end up being negligible. So what we're going to compare it to is the same series from n equals 1 to infinity of 3n to the fourth over divided by n to the fifth. So similar to this one, but a little simpler, so we can work it out. Now, if we simplify this, just like with integrals, when you multiply a series by a constant, in this case 3, that does not change whether the series is going to converge or diverge. It just multiplies every term by that constant. Okay? So what you can do is actually, just like with integrals, you can pull the constant on the outside of the series and it'll be the exact same thing. So it's just multiplying every term by 3 here. And then n to the 4th divided by n to the 5th reduces to just be 1 over n. Notice again, this one fits, much simpler one, a p series, because p is just equal to 1 there. And since p is less than or equal to 1, that means the series we're comparing it to diverges. But because it's not direct comparison, we don't necessarily know that this series is always either larger or smaller than the one we're comparing it to. It's hard to tell with these plus and minus, all these extra terms here. So we can't really use the direct comparison test. With a limit comparison test, we don't have to worry about which one's larger or smaller, or if that always stays the same or not. What we have to do then is just find the limit of the ratio of the two formulas. So as n approaches infinity. So with a limit comparison test, you go the limit as n approaches infinity. It looks kind of like the ratio test because it is a ratio, but we don't plug in n plus 1. We just use, again, a sub n will be our original formula, so that will be 3n to the 4th minus 2n squared plus 4 divided by n to the 5th minus n cubed plus 2 divided by b sub n, the one we compared it to, was just simplified to be 1 over n. But to make this simpler, remember dividing by a fraction, dividing by 1 over n is the same as multiplying by the reciprocal n over 1. So that's going to get rid of this part. And now let's substitute infinity. Well, if we substitute infinity, the term with the highest exponent here is going to matter, so that will end up being the 3 infinity to the 4th. The rest of the terms are going to be negligible, they're much smaller. And the denominator, the n to the 5th, the term with the highest exponent, so infinity to the 5th is going to matter. And then on this one, we substitute infinity for n, for 1. Okay. And then we can combine those on the numerator. So that becomes 3 infinity to the 4th times infinity is infinity to the 5th over infinity to the 5th. Then you can see that infinity to the 5ths reduce out, leaving you with just 3. And notice, we just want to see, this is our L here, our limit. Is that limit positive and finite? Yeah, it is greater than 0 and it's not infinity. So what that guarantees is both of these series have to both converge or both diverge. And since we already know by the p-series test, the one we compared it to diverges, that means our series would also have to diverge. So this one diverges by the limit comparison test and the p-series test. All right, let's take a look at one more using the limit comparison test. Okay, so for this one, notice the thing that's the most negligible as n goes to infinity is this minus 1 on the denominator. That doesn't affect it that much. So we'll compare to series from n equals 1 to infinity. Without that is just 3 over 2 to the n. All right, and then you could pull the 3 on the outside if you want, or just find the first 3 terms, since this is the one we're comparing it to, b sub 1, b sub 2, b sub 3, to see the pattern if you can't tell already what it is. So if you substitute in 1, you'll get 3 over 2 to the first, so 3 halves. If you substitute in the next integer 2, 3 over 2 squared is 3/4. Substitute in the next integer 3, 3 over 2 to the third is 3/8. So you can see what the pattern is. Each time it's being multiplied by 1/2, The numerators staying the same. The denominators will be multiplied by 2. So notice this is a geometric series. Whenever you just multiply by a constant or multiply by the same thing each time to get to the next term. So it's a geometric series. Our common ratio is a half. And remember with the geometric series test, if that's between -1 and 1, which it is, 1/2 is between -1 and 1, that means this series converges. So with a limit comparison test, again, we just find the limit as n approaches infinity of our original formula for the series, 3 over 2 to the n minus 1, divided by the one we're comparing it to, this one, which is the same as multiplying by the reciprocal, 2 to the n over 3. So even before we substitute in infinity, notice what happens here. The 3's just reduce out, right? And so what we're left with is 2 to the infinity divided by, this -1 is negligible compared to the size of 2 to the infinity, 2 to the infinity. Then those reduce out, leaving us with just 1. And the limit comparison test says as long as this is greater than 0 and not infinity, then these series have to do the same things. Either both converge or both diverge. And in this case, since we know already the series we compared it to is geometric and it converges, that means our original series would also have to converge. So we can say our series converges by the limit comparison test and the geometric series test. And that concludes the notes for AP Calculus on the topic of the direct comparison test and the limit comparison test.